last time, we had this problem on the board, right? I said, here's a circuit that you may need to solve. And you may have seen a circuit like this in circuits class, but in biomedical instrumentation, we're not just about solving circuits for their own sake. We're about solving circuits in order to do useful things, right? And I suggested to you last time, one useful thing that this might be good for is if this capacitor is a sensor, right? And then I said, well, how would you solve this circuit? And it turns out we need to know how to solve circuits like this, not just to make circuits with capacitive sensors, but as you'll see, to make circuits that can measure your heart rate. And in fact, to make all biomedical instrumentation. So what we're going to do now is we're going to take a little bit of a step back to circuits and review something called sinusoidal steady state analysis, which you sort of did? Yeah, you sort of did. And I'm going to review it. I'm going to go through it in a way that I think is very simple and useful. And then after we do that, I'm going to show you the power of it in biomedical instrumentation, right? I usually like to show you the use case and then the theory, but in this case, we're still working up the theory a little bit, all right? I want you to think of sinusoidal steady state analysis like a game, right? Someone here, who is it that likes Pokemon? Someone who came in before? Had a Pokemon? Hey, it's your Pokemon, you like soccer, you like Monopoly, you like Uno. Those are just games. To play the game, you need to know basic rules. Once you know the basic rules, the game can play out in a million different ways, right? But as long as you got the rules straight, you can always play the game, right? No matter what happens. So that's like sinusoidal steady state analysis. It's a tool. It plays out like a game. Here are the rules. You have some sort of system, which could very well, in our case, it's going to be a circuit. Right? There's an input, and there's an output. The input is always in the form of a sinusoid, so it would have this equation. Let's call it V in, it's a function of time, is equal to A times cosine of WT. And we reviewed last time, and this is the input. Okay. That we talked about last time what a sinusoid is, that it has an amplitude, it has a frequency that's governed by this, and we're going to start using the term W here, right? So these are constants, like A could be 1, and W could be 2, and this thing wiggles. All right? That's the input. If it doesn't have this input, you're not playing sinusoidal steady state analysis, right? It'd be like sitting down to play Monopoly, and someone shows up with a Pokemon card. It's not the same game. So this has to be the game, all right? We're only interested in inputs that look like this. The output has an equation. We'll call this V out as a function of time equal to B cosine of WT. So a sinusoid goes in, a sinusoid comes out, and the only thing that happens is that its size changes. And this is not an option. I'm telling you, these are the rules of sinusoidal steady state analysis. All right? Now, what's going to happen is the input is given. The system or the circuit is given. And you have to figure out the output. And if you figure out the output, you win sinusoidal steady state analysis. All right? So far, so good. But you'll notice something. If you got to figure out the output, well, what's the hard part? Well, you know that it's a sinusoid, and you already know its frequency, right? So when we say figure out, the only thing to figure out is B, and that's the first idea you need to realize. that to win in sinusoidal steady state analysis, the only thing you have to calculate is B. Now, by the way, I've left out phases. We're not going to, like there's phase, we don't need to worry about phase in this class, okay? So that's the game. And if you get the right B, you win the game. Now, right? You can see that. And we can write something else. We can say that, well, I'm going to say that A times, I'm going to call something called the gain. We're going to call A times the gain of the circuit or the system is equal to B. Sorry, B. Yeah. Okay? So the gain A times the gain of the circuit is equal to B. I'm going to call, and I'm going to use the symbol, let's say a little c to refer to that. So that means that A times little c is equal to B, or another way to look at this is B divided by A is equal to little c. And again, this here is the gain. I'm just writing the same thing over and over again, but I want you to understand that you need to know B, right? To know B, all you have to know is C, right? If A is 3 and C is 2, B is 6. And you have won sinusoidal steady state analysis. C, or the gain, is a function of the circuit. So for every circuit, you get a different C. So in fact, to win sinusoidal steady state analysis comes down to a simple task, which is to determine the C for the circuit. I mean, if you do this, you win. Because once you have C, right, then it's very easy to get B because you're just going to multiply A by it. And that is the game of sinusoidal steady state analysis. Okay, let's play the game. Let's play a few games, right? Let's play it out. Let's see how it goes. Let's go to the voltage divider. Right. And we did this last time, right? But we'll do it again, right? Slightly different way. And so the voltage divider, I'm going to have, do it like this. I have an input. I have two resistors, right? R1 and R2. I'm going to put the V out here. And this is my V in. Okay? Now, I need you to see that this here right, that's our system. Right, that's our, I want you to start thinking of this as a system. And the system has an input and the system has an output. So it fits, right? And I just want you to get used to thinking about this input-output kind of idea, right? You know what I mean? That's how we think about it that way. But you can see how it fits, right? Okay. Now, because this is sinusoidal steady-state analysis, I know that this has to be a sinusoid, right? I mean, that's not an option. It has to be the name of the game. You guys want to do this with variables or with actual numbers? Huh? With variables. Okay. So then we're just going to say that V in, we'll use the same thing, is equal to A cosine of WT. And if you like to work with numbers, call this a 7 and call this a 2. Call it whatever you want. But I just want to say this is just a wiggle. To win the game, we of course have to know what V out is. Turns out we know the equation for a voltage divider, right? And that equation is V out is going to be R2 over R1 plus R2 times V in. And we're used to seeing this for a DC input, right? But it is also the case that if this is a function of time and this is a function of time, it's still the correct equation. What I talked about last time is the only thing that has to work for this to work is Ohm's law, right? I could derive, as long as Ohm's law is working, and it is working here, you land here. It doesn't matter that it's a sinusoid. Ohm's law doesn't break for sinusoids. And we did this last time, right? Watch the video, like and subscribe. Let's plug in. We're almost done. So V out is there. Let's do time. So we're being explicit here. V out of time is equal to R2 over R1 plus R2 times the input, which is A cosine of WT. And we've won the game of sinusoidal steady-state analysis, because this is what you're supposed to do. Right? That's the game. The game is, what's the output? Right? Now let's do a little check here really quickly. The output is supposed to have a form of some number times the cosine that we put in, right? Well, here we go. There's the, you notice that here's the sinusoid that we put in. It remains protected. And then here we have a number, right? And this number is B, right? I could also ask you, well, okay, but what was the gain in this case, right? Which is this thing I'm calling lowercase c. What is the gain of this circuit, right? Remember, the gain is the thing that we multiply the amplitude of the input by to get the output, right? The gain is I want to remember, the gain is about the circuit. The gain doesn't know about it's a function of the circuit. And you can see that the gain is this. And I'm doing that as a dash line because it's a function of the circuit. So the gain is R sub 2 over R sub 1 plus R sub 2, right? That's the gain of the circuit. It is the C. So what do we have? We have an input, we have an output, we have a circuit. The circuit is characterized by a gain, which we call C. That's it. That's it. Let's do it with numbers, and I want to do it in a way that kind of helps us focus here on this C thing, right? So let's do it over here. I'm going to say that R sub 2 is equal to 2 ohms. R sub 1 is equal to 1 ohms. So now I want to know, what is the gain, also called C, of the circuit? Well, we believe that this is the gain of the circuit, right? So we would do 2 thirds. 2 over 2 plus 1, right? This is the gain of the circuit. What's interesting is that once we know the gain, you can ignore the circuit. Because to win the game of sinusoidal steady-state analysis, you just need to know the gain. Once you have the gain, you've won. So now we can say, okay, let's give a specific input. We're going to say, well, now V in is equal to 6 cosine of 12t. Now you have to say, what's the output, right? What is the output in this case? Well, we want to start thinking about this in terms of input times gain equals output. Input times gain equals output. Input times gain. So we could write 2/3, and here we have our 6 cosine of 12t, and this reduces to 4. And we have won, again, at the game of sinusoidal steady-state analysis, but now we're kind of thinking about this gain issue. You think why it's nice to have the gain, because if I were to suddenly change this to 12, it would be very quick for you to get to a new output, right? If I said 13 cosine of 16.5t, just a complicated numbers, not really. Just put the gain in front of it, and you get your output. That's it. What's really happening in the circuit is that if the V, if we were to plot it over time, if the V in is doing something like this, then the V out is doing something like this. Right? That's a graphical. Right, this is time. Right, that's a graphical representation, right? I'm going to leave this carved out. It's a separate problem here. This is a graphical representation of this, of that, same thing. And if I change these values, I think you could still win in the game of sinusoidal steady-state analysis. Yeah? Let's change the circuit. I did, I'm gonna erase this part here. I'm gonna say there's a resistor here, and now we have RA and RB. Okay. All right. RA, RB, R2, and I want to know what V out is. Right? I know you know how to solve this, but I want you to now just go back and say, okay, now what's the system? Now this is the system. We have an input, we have an output, right? And you need to play the game of sinusoidal steady-state analysis. I give you the input, and you have to give me the output. And what you'll see is, I can just go in here. I'm going to rewrite that we get R sub 2 over R sub 2 plus R sub A plus R sub B. What I did here is I took these two resistors and I combined them. What does it mean to combine them? It means to combine them from the perspective of Ohm's law. That's what it means. I don't physically combine them. So I treat them as one resistor with the value of RA plus RB. And then I reapplied my voltage divider equation where you have R2 over R2 plus this combined resistor. And now I have this. And well, now we're done because this just plugs into this, right? And we were done, right? We would insert this into there. Now I know what V out is. And if you wanted to do it with specific numbers, go ahead. Put 1, 3, 7, 2, 8, 21, right? Go ahead, put in whatever numbers you want. You have now won the game of sinusoidal steady analysis because you now know what the output is. And that's what that's the whole game. If I ask you what the gain is, you would say that this here is the gain. Also, the little c symbol. So if I said, what's the gain, you would tell me that. Okay? Now, in engineering, we like to use some terminology. It makes us feel fancy, right? Sometimes. And so I'm going to give another name for this. I'm going to call it the transfer function. Call it the gain, call it the little c, right? Call it the transfer function, right? Call it whatever you want as long as you call it. And you've maybe heard the term transfer function before, right? And we'll also, it's a useful concept. Why is it called transfer function? The input is being transferred into an output. The transferring is done by the circuit. But I don't need to know anything about the circuit. I just need to know the C. So the C is the transfer function. At this point, does it matter if there were 2 resistors here, or 1, or 7? It doesn't matter. The only thing I care about is the C. So once you know the transfer function, you have won the game of sinusoidal steady-state analysis, because the transfer function is the C. It's the same thing. So we will see about transfer function. Right? So far, so good? Yeah? So we'll keep playing the game. Go here. Let's play the game again. Okay. Let me walk you through this a little bit odd. Let's walk through it. In this case, what I would like to do is I would like to draw it out. I want to draw it. That's the easiest way for me to approach this. So what I'm going to do is I'm going to go back to the drawing. And the first thing I'm going to draw is V in. And it looks like a sinusoid. Now, how big it is, how fast it wiggles, I don't know. You know what I mean? I haven't actually told you that. But I should say that V in is a sinusoid. So it's A. It does have that form. Right? So the amplitude, we know, is, A to minus A, and this period, right, is going to be related to this W. But I haven't given you that, so I've just drawn it. But I have enough at this point to draw the output, actually. So I'm going to draw the output in orange. And I'll draw it, and then I'll explain to you how I got there. The output will look like this. Oh, no, it's not going to look like that at all. What am I doing? The output will look like this. And let's explain why. This circuit we've seen before, and it's called a comparator. And what it does is it compares the positive to the negative, right? If the positive is greater than the negative, then the output goes to some value, VCC plus. Right. If the output is less than the negative, it goes to VCC minus. Right? And so you can review the lecture, like and subscribe, on this comparator, right? Positive, negative. So this is the input. And so here, the input is greater than the output, right? Because it's positive. And so it's this. But as soon as this phase happens, the input is actually negative, so it's less than this. So now it flips this way. So I've drawn it. But sinusoidal steady-state analysis says that when the input is a sinusoid, the output is a sinusoid, right? That is the rule of sinusoidal steady-state analysis. But in this case, the input is a sinusoid, but the output is not a sinusoid, right? V out is not, does not equal B cosine of WT. It's not a sinusoid at all, right? Is that clear? So what does that mean? It means we don't play the game. It'd be like you're playing Monopoly and someone's like, and now I will build a house, off the board and charge you $100, right? They could do whatever they want, but that's not Monopoly. That's something else. And so the rules here don't apply. You could say, but the circuit's a real circuit. This is a real circuit. But this is not a sinusoidal steady state analysis circuit. You can't play the game. It's not that you've lost the game. It's not that you've lost it. It's not that you have failed to give the answer. There's nothing to play. We don't play with this circuit when we do sinusoidal steady state analysis. Does that make sense? You just don't play. You walk away. Say, I don't know what you're doing. It's not Monopoly, right? You can do it, but we're playing some other game. So the answer in this case is it's not applicable to sinusoidal steady state analysis. And there are some circuits, like this one, where a sinusoidal input does not produce a sinusoidal output of the same frequency. They will sometimes be called nonlinear circuits when people talk about systems. And we use them, but we don't use sinusoidal steady state analysis because the game breaks. Sounds good? One more quick one with resistors. Okay, just one more quick one. We'll use values this time. This is going to be 7 cosine of 2t, 1 ohm, 1 ohm, 1 ohm, 2 ohms, and here's our output, which is a function of time. Okay. So now we want to play the game of sinusoidal steady state analysis. We have an input, right? We have a system, and we have an output. And in sinusoidal steady state analysis, you have to figure out the output, but that just means to figure out the gain. It's the same thing, right? And we know that V out, if we call this, just to go through it quickly, we're going to say that V out is going to equal one voltage divider. So it's 1 over 1 plus 1, right? That's this voltage, right? We can write times V in, minus another voltage divider, 2 divided by 2 plus 1 times V in, right? And now we can take V in, and we can plug it in, and you can combine these things, right? Do that right? Yes. And you can combine it, and you'll get your answer, right? Dot, 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 dot. You can see that if I take this and I plug it in, we're done. There's some simplifications, right? This is 1, and you want to subtract 2/3, right? Right? And so on, right? But you're going to get an answer if you follow it through. I don't care about the answer, right, in this case. What I care about is that you're starting to understand how to play the game of sinusoidal steady state analysis, right? And in fact, if I said, oh, I want to be a little bit tricky, what's the transfer function of the circuit? Yeah, so now I say, well, I don't want the answer. Give me the transfer function. What is the transfer function of this circuit, right? It's just a fancy circuit, fancy word, right? Seems tricky. What's the transfer function? The transfer function is C, right? It's the thing that will multiply the input to give you the output. What is the transfer function of this circuit? Well, I mean, we can sort of combine these terms here, right? If you want to see it. So it's going to be, we're going to get 1 minus 2/3 times V in, right? So 1/3 V in, right? V out is equal to 1/3 V in, right? What's the transfer function of this circuit? Just 1/3. Right? Unless I made a mistake? 1/2. I did make a mistake. I saw the looks in your faces. You were like, huh? 1/2. Okay? So what's that? That's 3/6. 1/6? No. 3/6, 4/6 minus 1/6. Right? Did I do that right? 3/6. Yes, right? And so the transfer function is not this. It is minus 1/6. Right? So again, yeah, kind of complicated circuit, kind of complicated word, but the answer is just this number. And this number will multiply any input. All right? You want to do a quick test that this fits sinusoidal steady state analysis? Now let's take it times this input, right? So if you multiply this input times this output, right, in one step, you can see that V out is going to equal minus 7/6 cosine of 2t. This is okay. The input is a sinusoid. The output is a sinusoid. It's the same frequency, right? The W hasn't changed. The only thing that has changed is the B. And in this case, the B became negative, right? Because C happened to be negative. But that's fine, right? We're still playing the game of sinusoidal steady state analysis, right? In this example. And I knew we would because we just have resistors. And as long as you just have resistors, you can always play the game. Because resistors any complicated system of resistors will work for sinusoidal steady state analysis. And the reason is because Ohm's law always works. So everywhere Ohm's law works, sinusoidal steady state analysis works. All right? Sounds good? All right. So now let's do this one. Because this seems kind of like a sinusoidal steady state analysis problem, right? It does, right? Let's rewrite it here. Let's work it through. We have an input, and we have a voltage divider, but it's a voltage divider with a capacitor. R, C, V out, function of time. V in as a function of time, and we will specify that V in is equal to some sinusoid. Again, if you like to work with numbers, 2, 3, 4, 5, right? They're just numbers in here. So, and this is our right, that's our system. That's our circuit, right? So V in is going through our system. V in is going through our system, and it's becoming an output. So far, so good for sinusoidal steady state analysis, right? Okay. So far, so good. So then, of course, we have to answer what is V out. Now, as I went through last time, here's what you can't do, right? You cannot write that V out is equal to C over R plus C times V in. You cannot do that. Because, and the reason is because Ohm's law does not work for capacitors. Okay, this is not multiplication, it means does not work. You can't write to be specific, you can't write V equals IC, right? Putting all these X's. You can't do that. Because you can't write V equals IC, we're not going to end up here. And we covered this last time, right? So I want to be very clear that why you cannot do this. I'm going to now give you the simple solution, very simple. But the solution doesn't matter if you don't understand why you can't do this to begin with, right? This is not the equation that relates voltage and current across a capacitor. It's a different equation, right? It has a differential in it. But I said we don't need to worry about differentials in this class, right? And we're not. We're not. Okay? So, all right, I can't do this. So then how do I do this? Well, this is what you do. I'm going to show you how to play the game. How do you play the game of sinusoidal steady state analysis when there's a capacitor? You're still playing the game. We're not playing the game, right? It's like you're playing Pokemon, right? And you need to know how to add those energy things, right? Or you're playing chess, right? And you need to know how to castle, right? It's not that you're playing a different game, right? It's just that you got to like know a little bit more about how to play the game, right? But the game has not changed. So when you see capacitors in this game, this is how you deal with it. So we're going to delete the thing that's wrong. This is how you manage capacitors in sinusoidal steady state analysis. Okay, step 1. And there are only 2 steps. I always do that to you, right? I always say, here's how you do it, and there's only 2 steps, right? And then a little while later, I'm like cheating and I'm adding stuff, but okay. But in reality, there's just 2 steps. Step number 1 is, wherever you see a capacitor, I want you to write 1 over JWC. And I mean this literally right. This is not, I don't mean you to do like some sort of mathematical conversion here. I literally just want you to, wherever you see this, write this, right? So this means replace. Step 2, treat the, what are you calling it? Treat the capacitor like a resistor. And by what that I mean by is that you can now write Ohm's law across it. And we will walk through this, but once you understand this, you can solve any circuit with capacitors in it, specifically, but generally, but specifically for sinusoidal steady state analysis. And have you seen this before? You did, right? Now, if, I like it when you have like your little like antennas, like what is it? Your antennas should be up a little bit. This is odd. First of all, this W, is that W? Well, this W is the input, right? This is the frequency of the input, right? So why is it showing up inside the capacitor? That's odd. We'll talk about it. And then J. J is the square root of -1, right? It's an imaginary number. It's really odd, right? And yet, if we follow my formula, everything is going to be super easy. So we'll talk about J, we'll talk about W, but let's just do it. Let's just do it, okay? So we're going to go to this circuit. We can't write a voltage divider yet. So what we're going to do is we're going to apply this convention. And so wherever we see a C, you can cross it out, and you can write 1 over JWC. Right? And that's it for step number 1. Great, we only have one more step. Step number 2 is to treat it like a resistor. And what I mean by that is if it helps you, draw like a square around it. And just say, I know there's a lot of colors here, just say that this square is a resistor and its resistance is 1 over JWC. That is its resistance value. That's what this means. When I say treat the capacitor like a resistor, what do you mean it's not a resistor, right? It's a capacitor. I mean, from the perspective of Ohm's law, treat it like it's a resistor. So that means that we are in fact, we're back to the situation we had here. There's just two resistors. There's just two resistors, right? So the equation for, to lay it out, the equation for a voltage divider would be V out is equal to V in times, I'm going to say like this, I'm going to write R sub 1 over R sub 1 plus R sub 2. Now in this case, R sub 1, well, in this case, R sub 2 is just R, right? R sub 2 is whatever R is. So if R was 3, then so is that. What's R sub 1? R sub 1 is a resistor whose value is, put it in orange, 1 over JWC. That is the value of the resistor for this process. And you may not like the J and you may not like the W, and that's fine. But I'm just telling you that this is the value of the resistor. And so therefore, if this is a resistor with 1 over JWC, and this is a resistor with value R, we can write the voltage divider equation, right? We can go ahead and do it, and that's going to be, for this case, let's do it here, V in. So we have 1 over JWC over R plus 1 over JWC. All right, Vn, I'm going to write this curve. I can rewrite it, but I hope you know it. Vn times this, there's a block around it, right? There's a resistor here, right? These are just the resistance values. V out is equal to Vn times 1 over JWC, the first resistor, over R plus 1 over JWC. And you said, but wait, we couldn't do that when we had the C. You couldn't do that when you had the C because you're not allowed to write Ohm's law over it. Okay. This thing here is the transfer function. Okay, now I'm using the word transfer function. The transfer function takes the input and gives you the output. Specifically, the input times the transfer function equals the output. So it's important. It's just a multiplication. So if I have the transfer function, I take the transfer function, I multiply times the input, and I get the output, right? And so this is the transfer function. This here represents this circuit. This is the transfer function of the circuit, okay? Now, and this is where you're saying, but wait. What? What is this? What? You're supposed to give me the output B, right? The output B in terms of this, right? So you're sort of going to be in a situation where now you have to write, well, let's write it. V out is going to equal V in, so that's going to be A cosine of WT, and I'm just going to leave it in this form, so we're going to write 1 over JWC over R plus 1 over JWC. Put a box, all this here being the circuit, right? And it's not clear how to do that. So what do you do with this? There's a square root of -1 here, right? That's not workable, right? What is the square root of -1? It's not even real, right? So there's something missing here. So there is another step. But what I want to tell you right now is that this is the transfer function, okay? So I need to give you another step, all right? Should I move this out of the way? I don't know if I can even move this. Okay. So we need to talk a little bit about, JWC. Let's first talk about W, and then we'll talk about J. Okay. W, right, is the frequency of the sinusoid. Okay, it's the angular frequency, but it's the frequency. It's how fast it wiggles. It is this value here. So if it's 3 cosine of 10t, W is 10. If it's 13 cosine of 6t, W is 6. So this here is in fact coming from the input. Now it turns out it's also the frequency of the output because they're the same. So I didn't say frequency of the sinusoid input because I could have, but it's really the frequency of the only sinusoid we're talking about. So that value is inserted into here. All right? That's this value. That's this number here. If the input, for example, was 10t, I would insert a 10 and a 10. The capacitance is also, by the way, a number, right? So let's make the capacitance 0.1, right? So if the input is 10 and the capacitance is 0.1, 10 times 0.1, I would just get 1, right? So you see, once we understand that where W comes from, it's just reading off this number, right? This starts to, this whole thing here, and therefore this, it starts to simplify, right? Because, let me put a little star, right? Like, I'll put a dot over everything that's a number. This is a number. This is a number that we know. We know this number. 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 These are just numbers. 1 ohm, 2 ohm, 3 ohm, 0.1 farad, 0.1 farad, 10, 10. You see, so maybe it looks complicated, but you just put numbers. The only pesky thing is the J. Everything else is gone. That's where the W comes from. And so you're going to say, but you're telling me that the capacitor depends on the frequency? Yep. Yeah. The capacitor actually cares about what the frequency is. All right, so that's what the W is. So it may seem complicated, but it's just a number, just a number, just a number. All right. So this is the same thing. We can look at it here. We can look at it there. I want to ask you a question now. I want to do a thought experiment about if the frequency W was very big. All right. We'll go through this as a thought experiment now, and then we'll go through it again next class. Okay, but I want to do it once now, and we'll do it again. Let's say the frequency is very big. That means that the sinusoid is wiggling very, very, very quickly, right? Okay. So it means that W is right. W is a large number. W is a large number. Okay. So I have here. This is where W is sitting, right? So I have 1 over J, we don't know what that is, times WC, where W is a very large number. And I want you to accept that 1 over JWC, right, is therefore a very small number. Except, but J, yes, it's okay, even though the J is there. So like 1 over a billion is basically 0 if W is very big. The same thing applies here. 1 over JWC, 1 over J a billion C is basically 0. So for very high frequency, I can rewrite this as, if you go, 1, so it's going to be like 0 over R plus 0, right? If the frequency is big, this term here starts to approach 0, it becomes very small, simply because the W here and the W here and the R here, right? 1 over a billion plus R over 1 over a billion is like 0. So when the frequency is very big, the transfer function is about 0. What does that mean? It means that the input is being multiplied by 0. If the frequency of the input is very big, the output is 0. What about the other way around? Let's say if the frequency is very small, right? Almost 0, right? But not quite 0, right? But very, very, very small. Let's go through the thought experiment. And I know this is getting a bit complex, so we'll go through it again next time, right? But I want to go through it quickly right now. All right, I have here 1 divided by J times something, let's say 0.00001, right? Something, right? But when you have 1 divided by a very small number, the result is a very big number, right? Now this looks like maybe it's a billion, right? 1 divided by a tiny number gives you a big number. Same thing here. 1 divided by a tiny number gives you a very big number, right? And so I have like a billion over R plus a billion. A billion over R plus a billion, right, means that the transfer function is about 1. This term here becomes 1. Right? And we'll go through this again next time. I know it's a lot, okay? But what does it mean? It means that if you have an input that wiggles very, very quickly, right, that has a high frequency, the transfer function becomes 0 because of what this capacitor is doing. While if the input is very slow, the transfer function becomes 1. 1 just means that the input is the output. So this circuit cares about the frequency of the sinusoid. This circuit, its gain is dependent, right? We can write it another way. I can write that the C is a function of W, right? The transfer function is a function of the frequency. So when you insert capacitors into circuits, you suddenly create circuits that don't respond the same to cosine of 1t and cosine of 1000t. You suddenly create circuits that how they respond to a sinusoid depends on the frequency of the sinusoid. Sometimes they will let the sinusoid through. And sometimes they will not let the sinusoid through. In this case, a low frequency gets through. A low frequency sinusoid, come on through. You're good to go. Just go run on through. I'm not going to mess with you. That's what a transfer function of 1 is. But when a high frequency comes along, the circuit says, you're not passing, right? You are blocked. Or we could use another word, you are filtered. You are filtered. I'm filtering you out. Okay? That only happens because we have a capacitor. Sounds good? All right. So we're going to stop here. This is a big idea. So what I'm going to do next class is, I love doing this. I'm going to start all over. I'm going to start all over. I'm going to start with this circuit, and we're going to go through it all over again. We'll talk about this term here. I'll explain what the J is. We'll get into J. And we'll deal with, here I was able to avoid the J because I did these tricks where the J is knocked out, right? But we can't avoid the J forever. So we're going to get into J. I'll remind you about how to work with complex numbers, but I promise you, all algebra, okay? We're just going to work through algebra. And I'll show you how to deal with it from then on, okay? And so next class, we'll finish the sinusoidal steady state analysis game.